Hello and welcome to yet another podcast. So we're still in the midst of chapter 4, still kind of early. And we started with alkanes. We talked about how they rotate around sigma bonds if they're aliphatic. This time, what I want to do is look at them if they're cyclic. And so the freedom to rotate around bonds has been reduced. If you rotate around certain bonds, you may break the ring, so it doesn't allow for it. This also results in different sorts of what we'll call strains. There'll be a ring strain, just an inherent lack of stability associated with whatever bond angles are forced on the structure by the ring shape. And then something called torsional strain, where it starts to turn the twist and cause, the torque it causes on certain bonds or certain interactions will be elevated and causes an increase in the energy of the system known as a torsional strain. So the big thing is you can only have rings starting 3 carbons and above, or 3 carbons and heteroatoms combined. So 3 atoms total that can form multiple bonds can form a ring. And realistically, we will focus primarily on 5 and 6 membered rings because those are the ones that will show up in bio most frequently. The other ones are a little less stable, but we still want to go through all of the different ring sizes that are feasible to be seen in OChem. So I want to start with just revisiting what you got in geometry. So if I look at, let's say, butane. Butane has an angle of 109.5. That's what this is. So if I drew it precisely, you might have a CH3 connected to a CH2, to a CH2, to a CH3. But let's just say this carbon and this carbon are the same thing. So in other words, I want to bring it together and do this. So let's see how this folds up. So 109.5 angles that it wants to be end up getting scrunched down to 60. So if you remember, the total number of degrees in any, I guess, I don't want to say cyclic, but triangle, square, pentagon, any complete sided object, it'll always equal the number of sides minus 2. So 3 minus 2 times 180. So the total of all the angles inside a triangle, 3 minus 2 equals 1 times 180, 180. So all 3 of them must be 60 if it's a symmetric or equilateral triangle. Okay, again, I want to start with a comfortable angle of 109.5 and 109.5 for these. If I want to close this off, turn this carbon into this carbon, make this carbon this carbon. So in other words, instead of having 3 here and 3 here, make it 4 in a ring. This one comes over here, this one comes over here, and it closes out. You probably know those angles pretty straightforward, I'm assuming. 4 sides minus 2 would be 2 times 180 is 360. 360 divided by 4, 90 degrees each. These are not optimal. They're not 109.5. This is way off. This is off by a notable amount. We'll talk about some of the things this one might be able to do to help alleviate the stress and maybe make the angles a little bit better. It doesn't have to be planar. This one has to be planar, so it's stuck being 60. So 3-member rings, fairly unstable due to ring strain. 4-member rings, they exist, but they're not great. They're somewhat unstable. But once we start getting the 5-membered rings, again, number of sides 5 minus 3, or 5 minus 2, excuse me, equals 3, times 180, that's 540. 540 divided by 5 equals 108. So these angles are all the way up to 108. So if it contorts out of its plane, then you can start getting up in the 109.5 angle without too much trouble, meaning 5-membered rings start to push the limit, or push within the limit of what's acceptable within angles, within structures in OChem. So 5-membered rings, those are going to be reasonably common. The most common, 6-membered ring. So again, let's do the quick evaluation here. 6 minus 2 is 4 times 180 will be, 4 times 180 will be 720. 720 divided by 6, 120 per angle. So that's actually too high. So I would think at least 108 would be the best and 5-member rings be the best. But have to keep in mind, planar for 3, but once you go up to 4, 5, or 6 carbons in the ring, it no longer has to be planar. So this 6-member ring actually folds, and we're going to spend a lot of time discussing how it folds, but it can fold in a way where all the angles are approximately 109.5. Okay, so getting a little more detail about this. The three-membered ring, again, 60-degree angles. Problem with this is, in order to have the orbitals, so here's, let's say, one sp3 hybrid, and it could be sp2 depending on what the system is, but whatever it is, sp3 or sp2, either way, this hybrid here and this hybrid here are not along the internuclear region. They're curved out. So as the bond becomes less direct line overlap, you end up getting less electron density overlapping, and the bond becomes weaker. So the six-membered or the three-membered ring cannot have good overlap of the orbitals. Hence, I refer to that as a type of ring strain. So cyclopropane exhibits angle strain. That's what this is. And the other thing is, any substituents are on there. So what we mean by torsional strain, if I were to draw this structure from a side view, you would have, let's say it's just all H's on there. You have H here, and H here, H here, and H there, and H here, and H here. And as you can see from this perspective, these two start to interfere with one another. So these two H's will start to bump into each other. And although it's hard to see from my drawing, these three can all bump into each other, and these three can also all bump into each other. They're close enough to start interacting, which causes some sort of steric hindrance. And so this structure will try to contort, if it can, rotate these down and these up, and that's what's known as the torsional strain. Okay, I'm going to say strain in general, and if you just have an idea that six-membered or three-membered rings, excuse me, sorry to keep doing that, are unstable due to that strain, that's exactly what we're fishing for. Okay, let me get rid of what I've drawn so that I can bring in the four-membered ring. So four-membered rings seem like they should be a little bit better. And like I mentioned, they can start folding out of the plane slightly. So if you look at this structure, it's not perfectly square. You have these two sticking slightly up and these two sticking slightly down. But again, you start running into these H's here. They're not super close, but they still overlap. They're still eclipsed. Those were eclipsed. The other H's, which I'm going to refer to as equatorial, we're going to use that as kind of the equator of the structure, and these are axial. The axials interfere with one another, and because they don't want to be eclipsed, one's going to rotate a little to the left, one will rotate a little to the right. When it does it, it causes strain on the structure. So again, torsional strain and angle strain. Those are the two that are popping up within this. It's not the optimal angle for the hybrid orbitals to overlap in the sigma bond, and torsional strain because we don't want eclipsing interactions. So again, it's not as big of an angle strain as the first one, but huge torsional strain because of that eclipsing phenomenon. Okay, so we march on. So those are the ones that we don't like. Now it's time to look at the ones we do like. So the five-membered ring can actually fold into this somewhat puckered thing. So these four we can assume are somewhat planar. This angle is going to pull out a little, this is going to pull out a little, causing these to go closer to 109. 109 here, and this one goes up, and it doesn't look like 109 from this angle, but it can achieve that as well. So you can start getting closer to optimal angles, but again, you have somewhat of an eclipsing interaction here and here, and here and here. And so as it starts to twist and turn to try to avoid those interactions, it's going to fold, and eventually you're going to have some interaction. So as these two start to become less overlapping, these become less overlapping, you start to run the risk of making these equatorials start to be a little more eclipsed or closer to eclipsed. So five, although the angle looks good, still offers a lot of torsional strain, so it's not as good as a six-membered ring. All that buildup, all that to simply say the six-membered ring is the best one. Okay, so again, torsional strain and ring strain, or angle strain, you're going to time this overall ring strain. 5 is better than 3 and 4, but it's still not perfect. But you do find it in a lot of biological molecules, especially when you start having sp2 hybridized carbons or nitrogens in the ring system. So the most stable of all, again, 120 is not ideal, but when it folds in a way where this point comes up, let's say, this carbon goes down, this one kind of slices up, this one kind of slices up as well. So up, down, down, up, down. That's how we've drawn it. So this one went up. Let's just say those are matching carbons. These two are a little bit down. These two right here and here, excuse me, are up. This carbon right here goes down a little. When doing this, a couple things happen. Number one, the angle gets closer to 109.5, which is great. You have the equatorial situation, like I mentioned before. So on the kind of the equator here, kind of the equator, kind of sticking out, out, and out. So these are not necessarily, planar is not the right word for it, but if I had a ring around the system, like a loop, they would all come close to passing through it. I have 3 that are axial up. And fortunately, they are 1, 2, 3. So there's a carbon between them. So 1, 2, 3, 1, 2, 3, and then 1, 2, 3. So they're spaced far enough apart that it doesn't become as bad as what we saw before. Neighboring atoms are eclipsed. These, we're still going to call them diaxial interactions, but because they're not on neighboring carbons, we can't truly say they're eclipsed. But they are, I guess, going to interfere to some degree. But hydrogens are small enough. This isn't so bad. Same thing with the ones that are down here. Not as bad because they're not right next to each other. There's a carbon separating them. So this is going to be a major focus of what we do. It's going to be called the chair conformation. And so I want you to know the concept of torsional strain, where things don't want to be eclipsed. And then angle strain, meaning you want to have the optimal angle for whatever the hybrid is, 109.5 for sp3, 120 for sp2. But you also want to know what's going to happen with the groups that are on whatever ring structure you're dealing with. So this is a really bizarre looking Newman projection, but it's actually pretty helpful. So if we were to look at this structure right here, if I call this the point carbon right here, and this one the ring in back, then on the other side, I'll make this my point carbon, and this my ring carbon, point and ring. So kind of a weird Newman to draw. But if I look at this front carbon here, I'm coloring it in. I don't know if you can see it because I'm doing it in black, and that's not working, but this is going up and down. So it's going up and going down. So there's an H sticking straight up. That's this one right here. And this H is coming out at you. So this is kind of a good perspective. It's hard to tell, but this one is actually the closest H to you. And then on the back carbon, from this yellow to this green, we're passing through this carbon, which represents this one, which has one straight down. So this H right here is this blue one. And this H going back is this H going back behind. So this is furthest one away from you. So this doesn't really do justice to these two H's, but this does. As long as you can visualize it. This one's coming out at you. So I might want to actually emphasize it by being bold, and this one's going back behind. So this is more the way those hydrogens appear. So equatorial, 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 axials, and axials. And they're far enough apart from one another that they don't necessarily bump into each other. If I replace the H with something bigger, there's a risk they can bump into each other. But so-called diaxial interactions are not so bad for hydrogen. So this is a nomenclature experience. Torsional strain, angle strain, and then this concept of axial H's and equatorial H's on a ring structure. Sorry, I should leave my pen there a longer time. 1, 2, 3, 4, 5, and 6 equatorial. 1, 2, 3, 4, 5, 6 axial. So every carbon has an equatorial and an axial. You also note that if equatorial is down, axial is up. When you move one carbon over, now equatorial is up and axial is down. Equatorial is only slightly up or slightly down, whereas axial is all the way down or all the way up. So we'll go much more in this in detail as we go down the road. But this is known as the chair conformation. Once upon a time, probably in the 60s when this thing was named, this was considered to be a cool little recliner chair. So they call this the chair conformation. We'll look at a couple other versions of the six-membered ring, but chair conformation is going to be your most stable. One thing that hopefully you sit and contemplate, does it necessarily have to be point up on one side and point down on the other? Or could it be point down on this side, point up on this side, and just invert? The answer is going to be yes, it can invert. So just like we looked at gauche and anti, eclipsed versus staggered, and we looked at linear aliphatic alkanes, those are called different conformational isomers or conformers. The chair is going to have multiple conformations as well. So with that in mind, I will just put this on to the next podcast. But this is where we'll start. So we're going to draw chair conformations for the next one. So see you very, very shortly. So thanks for tuning in, and tune in soon.